We are going to talk about transforming these sine and cosine functions one more day. Tomorrow we'll move on to what the secant, cosecant, tangent, cotangent, those four graphs look like. But at the same time that we mess around with those, we can still transform those. So if we struggle with the transformations and we move on, we're moving on to new graphs that we can do the same transformations in. So the concepts will be the same. Before we get into anything, I want to kind of explain to you a reason for us having these graphs, okay? Being able to construct them by hand, and obviously, constructing them by hand is kind of like an old world technique or process because we do have technology that does this for us, right? But I want you guys to understand that when I'm in a pinch of solving an equation, that it's trigonometric, okay? So if I have, for instance, the question, when does, sine of 2x equal 1/2, okay? Because that will be a question that we ask here pretty soon. And you have to go by hand and do that, okay? Without graphs, okay? We go through the analytical algebra, the handwork, the handwritten work. What does that mean to me? How can I know that I've done it right? Well, we can grab our calculator or whatever program you want to use that will graph these for you, and you graph the left-hand side, and then you graph y equals the right-hand side. And just like any other equation that we've ever come across, the left-hand side and the right-hand side, where they intersect is the solutions to that equation. Does that make sense to everybody? Okay. So this A value, the x coordinate of that A value, so 0.26, if I put sine of 0.26 in here, it should spit back 1/2. Does that make sense? Okay. So I want you guys to be able to solve some equations eventually, but understand, okay, when I solve those using algebra, can I have a graphical approach? And we do. And but I think it's important that we understand how the graph of sine and cosine work and relate, so we can better interpret why we have maybe how many solutions are we going to have to that equation. You're going to have an infinite number of solutions, okay? And understanding the sine and cosine curve and how they behave provides insight on maybe why we have an infinite number of solutions, and then again how maybe we can learn that if I know what A is, I essentially know what all my other solutions might look like, okay? Because does this point here, does A, let's see if I can, A, and then let's say we look at this point down here of B, do they kind of look like the same point on the curve? And obviously they're in different locations, but they are, let's look at that distance. The distance between A and B, in this case it's 3.14, which would be what for us? That's pi, right? Okay. If this was just, let's see if I can just change this to x. Okay, now I don't want B, I want, let's say, this point over here. So let's look at C. So let's look at the distance between the x value of C minus the x value of A, and the distance between them is 2 pi, right? Okay. So every point that is actually A plus a multiple of 2 pi will give me another solution. Does that make sense? So if I look at, so that's C, come back here, maybe point D right here where my cursor is going to be the x coordinate of A plus 2 pi plus 2 pi, right? And you get another solution, I would have the x coordinate of A plus 2 pi plus 2 pi plus 2 pi. And you get another one, add 2 pi. You get another one, add 2 pi, right? So they mimic one another. They're repetitive in regards to multiples of pi, or 2 pi in this case. So that's kind of where we're going to take this stuff later in this chapter. So I think it's a good idea to understand what these curves look like initially. because it's an alternate approach to solving those equations. All right, so getting into then just a specific example. We did some of these yesterday with you guys, and I want to kind of take a step back and do yesterday. I think the one we did had like 3 or 4 transformations in it. Maybe that was too many at first introducing these. So let's kind of take a step back and focus on just maybe 2 or 1 transformation at a time. So what I want to do, I want to graph y equals, let's go just 2 sine of 4x. 2 sine of 4x. Okay. Now, it's not a big deal here because there is no plus or minus in regards to the argument here. We're not moving it left or right. But you might want to get in the habit of just saying this is 2 sine, factor your 4 out, get your x by itself, because we are going to want to do that here in a little bit with our other functions. I think it's a good idea. Now you don't have to draw this out every time. Maybe you've got it on your notes, or I've seen people in the past just have 2 little index cards, or 1 index card. On the front they have the sine graph, on the back they have the cosine graph, and whenever they're doing these problems they just have that index card with them so that they can kind of mimic the relationships. Okay, so we've got the sine function. I'm going to go y equal, I'm just going to graph down here y equals sine of x. And we know that thing, what's the period for sine? 2 pi, okay? So I'm going to have, for the sine function, we start at 0, 0, and we'll finish at 2 pi, comma 0. We know halfway between, we should pass through pi again, okay? Now, what's nice about that, and this is going to be mimicked every single time you see a sine curve, or no matter what the transformations are, you're going to break this thing up with your x-intercepts into 2 equal regions, 2 equal intervals. All right? And inside those intervals, halfway inside those intervals, you're going to have some new points. Okay, halfway inside, so at pi over 2 and 3 pi over 2, the first one you're going to reach your maximum, and in the second one you're going to reach your minimum. And remember, all those ordered pairs come straight from the unit circle. Okay, so I'm always going to have that thing with me, okay, and always thinking about that thing. Because no matter what function I'm trying to graph, if it's got sine in it, no matter what the amplitude is, no matter what the b value is, no matter what the left and right or up and down movements are, that relationship of those 5 points is going to be maintained. Okay, kind of the symmetry that we see with those 5 points is going to be maintained. So I'm going to kind of use that here in graphing. Graphing 2 sine of 4x. I think the first thing you guys are probably going to want to do is look at that value there, that 4, and we know that's what we're calling b, okay, from our kind of general format of a sinusoidal graph. And that is going to impact your period, right? The period of any sine curve or cosine curve is 2 pi divided by that b. So right now it's 2 pi divided by 4, which ends up being pi over 2, right? Okay. So what does that tell us? It tells us that this graph down here is going to occur between 0 and pi over 2 now. So when we graph this, I'm going to come up to my x-axis and put my starting point at 0. I'm going to define where I want this thing to end. Maybe and I'm just choosing this arbitrarily. Okay, put pi over 2 somewhere, and now my graph is going to oscillate between 0 and pi over 2. It's going to finish one complete cycle in that interval. Okay, And you can put pi over 2 anywhere you want. Does that make sense? I'm a person, for the most part, when we're doing these, I don't try to set up my x-axis all at once. Because I might set up my x-axis in terms of like pi over 6 or pi over 12. In fact, pi over 12 is actually a really nice one to use because it's going to hit your pi over 4 multiples and your pi over 3 and pi over 6 multiples. But if I set it up using pi over 12, I might go through this graphing and only use 2 of those points. Does that make sense? And I did a lot of unnecessary work maybe for developing the graph. So I'm going to do pi over 2 and 0. And I know that down here, because it's the sine function, that point of 0 is going to correspond to that point at 0, right? One complete cycle or one complete period is going to put my sine function back at an x-intercept, and that point should correspond to that one. Does that make sense, everybody? So if we're going through that correspondence process, this point here was halfway, right? So there should be one up here that corresponds halfway. What would that x value be halfway? Pi over 4. Okay, so I should have a point there. And again, that corresponds to that one. Is that something we can do? Okay. Now, what does that do for us on our graph? It creates 2 intervals. It creates that interval there and that interval there, right? Okay. Using then that correspondence, halfway in between this green interval down here on the parent function, we reached a maximum, right? So halfway in between here, we should reach our maximum. Now, what would halfway in between 0 and pi over 4 be? Yeah, multiply it by half, right? Or divide it by 2. Should be pi over 8. I'm going to reach my maximum, so I'm going to come up here and put my maximum point. I'm going to let 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Now, and this could have been something you've done at the beginning, or you can wait until the end, or you can do it now. But my maximum is going to be based off that number there, right? That's a vertical stretch. So it's going to be a height of 2, and that's going to be negative 2. Okay? Now in this blue region, halfway in between, you reach your minimum. All right, now I think it's important to be able to know what that ordered pair is. What is that x value? Well, this thing right here, when you plot that first point, that first maximum, this interval that you've created is kind of your counting tool, your index that allows you to move throughout the graph. So pi from one x value to the next. So pi over 8 plus pi over 8 would be 2 pi over 8, right? And then that would be 3 pi over 8. And once you have those points, it's just then a matter of connecting with a smooth curve. Okay. Now that I've got that smooth curve, let's say the question said graph 2 complete periods. Okay. And just because I don't have any room to the left-hand side of my y-axis, my negative x-axis is off the string, let's put one more period to the right here. Okay. And this, guys, this is how I would do this. And I think you're probably going to want to kind of follow kind of a similar procedure. That distance right there is the length of one period, right? That green distance. Can I somehow copy that distance, lay it down here, and now know that that distance is also pi over 2? Does that make sense? So what's pi over 2 plus pi over 2? Gets me to pi, right? Okay. And now essentially I'm gonna repeat the process of taking that green interval, cutting it in half. Okay. Well, halfway between pi over 2 and pi is 3 pi over 4, right? Maybe you don't like that. Maybe you don't like trying to develop what that halfway is. Can we keep doing this? This was pi over 8, right? So that got me to 3 pi over 8. Pi over 2 is 4 pi over 8, right? Do it again. There's 5 pi over 8. Here's 6 pi over 8. And then one more time would be 7 pi over 8, right? And if you want to reduce, I reduced the 6 pi over 8 to 3 pi over 4, but it doesn't matter. If you want to leave it unreduced, you can. But that creates now my x-axis over here in regards to one more cycle for this function. Now, think about your parent function. My parent function starts at an x-intercept, finishes at an x-intercept. Halfway in between, I have another x-intercept, right? And now would you guys agree that there's our green interval, there's our blue interval, halfway in between the green one you reach a max, halfway inside the blue one you reach a minimum, and now you have kind of effectively cut and pasted your sine curve. And that's 2 full periods of 2 sine 4x. Is that all right? Okay. Now, because we don't have the sine function drawn in there as the same scale, okay, I kind of want to show you graphically what that 4 is really doing to our curve, okay? You can maybe think about it, you know, I could maybe in your notes you might want to write this. We know for the parent function, that should be an x-intercept. That should be an x-intercept, okay? And this should be 1, should be a maximum, okay? So if I just graph that portion of the parent function, it's just 1 maximum kind of bump, right? Okay. Keep going out to 2 pi, it would kind of look like that. Does that make sense to everybody? Do you see then that the one that we did with the 4x is a horizontal compression or a horizontal squeeze? Does that make sense? Okay. Obviously a little bit easier to see here, so let me type in sine of x. I'll just put the parent function in first. And I like to make that very, very thin line, kind of like almost a ghosting of an image. You can't really see it very well. I don't want it to create confusion of the one that we're really interested in. We're interested in sine of 4x. And there's actually 2 sine of 4x, but we'll just do 1 sine x. Or sorry, 1 sine of 4x. And I get that. Okay? So you see that if I just look at both these between, let's look at this between 0 and 2 pi, and then look at this one between 0 and 2 pi, okay, you see that the curve is we go through more cycles, right, inside that interval of 0 to 2 pi. And that 4 tells me that basically in between 0 and 2 pi, I'm going to go through 4 different cycles. Does that make sense? So it's I like to view it this way. If I were to take, you know, the entire sine function without the restriction, okay, so don't have the restriction. I like to think about taking it and saying, okay, I'm going to put, I view it kind of like a spring, and I put my hands here and here, and if I push my hands together, you see how that spring would kind of coil up on itself and create more compressed peaks and valleys. So a number greater than 1 will do that for that B value. All right, so that's something to think about. When B is greater than 1, we get this compression. Okay. Just another thing that we can talk about is, do you guys remember? Let me just graph maybe a function that we're more familiar with. If I just do square root of x, you guys remember if I multiplied the entire thing by a negative, what axis that flipped it over? Flips it over the x-axis, right? Okay. But we also had the ability not just to multiply the entire thing by a negative, but we could actually go in and multiply the x by a negative, right? What axis is that going to flip it over? Flips it over the y, right? So can't we do the same thing with this one? If I have sine of 4x, what happens if I multiply the x by a negative? So maybe do that. I could have just put it with the 4 as well, but it does. Okay, because my interval is outside. So let me just get rid of the interval. So let's call this g of x. What? All right, we'll just start it. G of x equals sine of 4 times negative x. How does that relate to sine of just 4x? Okay, so sine of 4x, the one we graphed, is the orange one, right? If you take the orange one and you reflect it over the y-axis, do you think it becomes the purple one? Yeah, okay. So that negative, we could do that, okay? And sometimes you might not see it written, I've got it written this way, but you could also write it that way. Okay. Now I want to go through a little bit of it just to show you something to prove a point to you. I want to go through a little exercise here that's going to take the purple one and move it on top of the orange one. Okay. If I was going to take the purple curve and move it on top of the orange one, okay, I need to move the purple one left or right, correct? Okay. Now I need to move it left or right. So let's look at that point right there where my cursor is. I would need that point to go to that point, right? Does that make sense? Or that point to go to that one. I need these peaks to match up, okay? These maximums to match up. So the distance that I need to move them is what? Pi over 4? Does that make sense? Okay. So I'm going to take this function. Now, because I've got the 4 stuck to the x right now, I'm actually going to factor that out. And then I'm going to, let's move it to the right, so it should be minus pi over 4. Put one more parenthesis. And you see then that it did take that and transfer it to the same spot, right? So if I highlight, you see highlighting the red one kind of shows you a red curve, highlighting this one shows you the purple one, right? They're the same thing. Okay, well, if I look at this one, okay, so sine of 4x, let's do a little bit of algebra with this purple one. Sine of, it'd be negative 4x plus pi, wouldn't it? Does that kind of make sense? So this might be the way you see it in your homework. This would be the way we would want to write it so that we can actually graph it and understand the transformations. But what I want you guys to understand, those two things are the same curve. Okay? They're the exact same thing. They're different equations that provide the same graph. Let's do this. What was our period here? Our period was pi over 2, right? Let's take this one. Control C. Control V. And let's just add pi over 2. And it gave me the same curve, right? Okay. What's pi over 4 plus pi over 2? All right, let's do it this way. What's negative pi over 4 plus pi over 2. Just pi over 4, right? Okay. So let's take that. Okay. Do a little bit of work. Let me write something down here. So right now, this thing here, this purple one I got highlighted, would actually be sine of negative 4 x plus pi over 4, right? Okay. Well, if I distribute my negative through, doesn't it become negative 4x minus pi? Is that different than this one? So let me see if I graph it. It's algebraically it's different, but graphically is it the same thing? So up there we have 4 different versions of the same graph, right? How many versions do you think we could have? Infinite. Okay. We have just an infinite number of versions just based on being able to add our period multiple times over and over. Because if we have, just think about this. I don't know if I'm going to be able to do this the way I want to. Let me think. Sine of 4 x. Let's do this. 4 times a x. See if this will do what I want. Oh, I want this. 4x plus a. All right, so you can see that, I can take that a value and I can start moving it. And if I make this thing like 50 pi, there's a lot of different, that's really fast. All right, just to give us a reference point, that point A. We could start moving this thing and see there that they overlap, right? So that would be another version of the equation. And I keep moving it, and they go again, right? It's a different version. And now taking some liberty, they're close enough, right? So they would have eventually have overlapped. That's a different version. So just by adding our period over and over and over and over again, we will basically be sliding the graph left or right to match up with itself again. Okay. So that being said, if I were to give you guys a graph and say write the equation of this graph, there's going to be a potential that if there's 40 people taking the quiz, there's going to be 40 different right answers. All right. Where if I did that for a parabola or a cubic or something like that, there's only one answer, right? If I ever ask you to do that, okay, WebAssign might ask you to, but they'll give you restrictions. Because obviously WebAssign doesn't have written in the background the coding to match up infinite possible solutions, right? So they'll say, use sine only, okay? Because we could actually mimic that purple graph with a cosine function too. Because we know cosine and sine are just translations of one another, aren't they? By pi over 2. So they'll say use only sine, and then they'll say using maybe the smallest possible horizontal distance for a translation. And that will then get everybody to write the same answer. But that's what I wanted to show you guys. I want you to understand that's kind of a unique situation for equations that we really haven't seen, or function graphs that we haven't seen, that they are periodic, therefore you're going to have maybe multiple ways of being able to write them or define them. Let's do, so that's when we have this number out front of the extra b value to be bigger than 1, okay? Let's do one where it is less than 1. So let's look at y equals, let's do cosine. I don't know if we've done cosine too much or at all. Cosine of 1/2 x. Okay. So got our parent function down here. We go y equals cosine of x. We know that unit circle goes from 0 to 2 pi. So that's our beginning and our ending for the period for the cosine. But this one's a little bit different. The cosine, remember, is plotting the x values off the unit circle. So the first x value with a distance of 0 radians would be an x value of 1, wouldn't it? But because it's still a unit circle, it's still cyclical, so it's going to start at 1, it's going to go around and change, but it's going to get back to 1 eventually, right? So at 2 pi, we're back up at a height of 1. And now we can create the same symmetry halfway in between, which is at pi. What's the cosine for pi? On the unit circle, the x value would be what? -1. Okay. So there's the idea that halfway in between, on the sine, we reach an x-intercept. Halfway in between on the cosine, you reach a minimum. But do those 3 points still create those 2 regions? Okay. Now, for the cosine, we need to travel from this point to that point, right? What will you pass over when you do that? X-intercept, right? The x-axis. And the place that happens is the halfway mark. So pi over 2. And then go from the -1 to +1 in the purple region. Same thing happens. Halfway, you pass through the x-axis. So there's our parent function, roughly. Okay. So I'm going to use those relationships to help me do cosine of 1/2 x. Well, if I go y equals cosine of 1/2 times x, that 1/2 is our b value, right? So I'm going to come to the side. I'm going to do period is 2 pi, because that's the period of the parent function, divided by that b. Well, what's 2 pi divided by 1/2? 4 pi. So now our cosine, right here, where the whole thing was happening between 0 and 2 pi, now the whole thing is going to happen between 0 and 4 pi. Okay. It's a 1 cosine. Okay, so that's our maximum is going to be 1. Our minimum is going to be 1, -1. So using that correspondence, we know at this point here, that point should match to that point there, right? That's where we start. We'll finish at the same height. So that point there corresponds to that one. What's going to be the halfway mark for 0 to 4 pi? 2 pi. And that's where we reach a minimum, right? So that point there corresponds to that one. This okay with everyone? Okay. And I'm going to delete those lines, so wait a minute. Now, if we look at that point there, that pi over 2 mark, that x-intercept, that happened halfway in between this interval here, right? That would be a kind of analogous to that blue interval in our parent function. So halfway in between would be pi. So we'll get that point there. And then in the purple region, halfway in between. So halfway in between on this region would be 3 pi. And now we've got that set of points to create that smooth curve with. Something, guys, if you ever forget, I mean, this is, we're using this strategy, this technique to graph using the kind of correspondence of the points for the parent function. But if you ever forget, can't I just evaluate? Can't I say, okay, well, if x is pi, what do I get? Plug in 1/2 pi, I get cosine of pi over 2. Think about the unit circle, what is the cosine of pi over 2? 0. Okay. and that's why we get our parent function as 0. Just kind of things to think about as we're graphing these using different techniques. There's still the idea that this is a function. You can use input values, being your x-axis, to get back output values. Okay. So that being said, let's now these two, obviously they look kind of the same because we don't have the parent function of the cosine graphed on here. The parent function of the cosine is going to look, do it here in green. It's going to do one cycle between 0 and 2 pi. So the parent function of the cosine would actually look something like that, right? Does that make sense? So you see the blue one would be the stretched version of that, the horizontal stretch. But this point here, because x is 0, that point is kind of static, right? So it's like somebody took maybe a nail in that point, and it's not going to be able to move away from the two-dimensional plane, and somebody took this point and pulled it to the right, so everything else gets pulled to the right in the same proportion. Does that make sense? Okay. So what I want you guys to understand that when we look at our b value, when I go y equals, whatever my trig ratio is, so a times, let's use sine right now, of b, I'm going to write it this way, x plus c plus d. That b value, okay, if b is greater than 1, it's a horizontal compression. If b is between 0 and 1, it's a horizontal stretch. Okay. And understanding that, you don't have any understanding right now of how we're going to solve these things algebraically, how we're going to solve equations algebraically. But that understanding of what our b value is, whether it's bigger than 1 or between 0 and 1, is going to provide me insight on how many solutions I'm going to have to some equations later on when they restrict a interval for my equation or for my solution. Which is something to think about. Maybe I'll give you a picture of this. Let's say that I have, let's get the x-axis here to be in, let's go pi over 2. Let's just say that I have the graph y equals sine of x. But I only want to look at that between 0 and 2 pi. What f of x equals sine of x. 0 is less than x is less than 2 pi. Okay, so we just have that graph there, right? And if I ask you, let's look at that and say, okay, if this was an equation, let's say, when does this equal 1/2? Okay, so that information there, that graph would be the question, when does y being sine of x equal 1/2? How many spots does that do that in between 0 and 2 pi? Yeah, it's equal there, and they're equal there. There's only 2 spots. But if I do this, if I make that a 2, now how many spots is sine of 2x equal to 1/2? 4 now, right? Okay. What if I do this and I go 0.5? That goes back between 0 and 2 pi. Now it goes back to 2, right? But what if I go 0.25? Now it's only how many solutions? Just one, okay? So understanding what that B term is later on will provide you, and you understand what it's doing to the graph behind the scenes, will provide you insight on how many solutions you might have on a predefined interval, okay? There is the ability, you guys do have the ability to graph these things on your calculator. The one thing I just need you to know is that when you're doing it on your calculator, you need to be in radian mode, okay? Your calculator will not graph the curve that we're looking for in degree mode, okay? So just make sure of that. The only thing that kind of stinks, and it happens with all graphs that you use your TIA 384 with, it doesn't really put numbers on here, right? It doesn't label your x-axis and your y-axis, kind of like GeoGebra does. Or if you're using Desmos, Desmos is a good program in regards to these. Not overall. It's a terrible program overall. But if I grab, Sin of X does a good job there. I can click it, and it's going to give me those key ordered pairs in a nice format, okay? Now, I don't know. I haven't messed around with it enough. I don't know if I can change the x-axis on this like I can in GeoGebra. But it is nice that it does give me those key critical points in terms of pi. I don't know if maybe I change that to 2 if it'll do the same thing. Yeah, it does. That's kind of nice. Yeah. Finally, something useful with Desmos. We have time. I want to do one more just quickly. Whether we graphed or not, I don't know if we'll get to that stage, but because I think, guys, with this stuff and being successful at it, the only way you're going to really get good at it is if you practice it. See as many examples as possible.
Pardon the interruption. This is just a reminder that the students in the following teachers' Wildcat times will need to report to the gymnasium today. Mr. Blevins, Mr. Hain, Mr. Fay, Ms. Ungerfer, Mr. Gillette, Mrs. Ellington, Mr. McCoy, Mr. Steidel, Mr. Grimm, Mrs. Coles, Mr. Mock, Mr. Wilkerson, Mr. Rube, and Mr. Gomez. Again, the following, those teachers' Wildcat times will need to report to the gym today for Wildcat time. Thank you.
Do you know why?
Juniors are taking the ACT on the 20th, so they have to provide us instruction for people who have never given the ACT on how to proctor that. That's what they're going to do with the teachers. You guys are going to, it's just kind of a holding tank for you guys, because teachers are going to be somewhere else. All right, so if we do this one, now this is a little bit different because it's there's a horizontal shift here, right? Now your horizontal shift is not going to be pi over 2 units, okay? Because you need to factor that 3 out. So I factor the 3 out, I'm going to be left with x minus. Now factoring a 3 out, factoring is just division, right? So divided by 3. What's the same thing as dividing by 3 but using multiplication? Multiplying by a third, right? I think that's easier because now it's going to allow me to get this value transformed pretty easily. What's pi over 2 times a third? Pi over 6, right? So that gives me that is my left or right, and in this case it's right. It's going to give me that movement, okay? This 3 is still the b value. So when I say my period is 2 pi over b, it's 2 pi over 3, right? So that being said, when I come to my graph, I'm going to set up my ending point for the cosine at 2 pi over 3. Now, still got my same starting point of 0. I want to write my x-axis in regards to denominators of 6. Because when I start transforming points and moving them, it's going to be really nice if all my x distances are 6. Does that make sense? Just kind of, if I had to move it by force, I would want my x-axis in terms of force. So I'm going to write this as 4 pi over 6. So what's halfway then? 2 pi over 6. What's halfway there? Pi over 6. And then this would be 3 pi over 6. Now, if you want to reduce those, you can, but it makes it nice because now using the correspondence here, I should be at a height of 1 right there at 0, back to a height of 1 at 2 pi over 3, right? At 2 pi over 6, I'm at a height of -1, and then halfway in between, I'm back through the x-axis, right? So I'm able to take the correspondence of my parent function to get these. Now, these points are not the ones I really want to graph because I haven't moved them yet, right? But now because my x-axis in terms of 6s, it's really easy to see at that point there needs to go there. I don't know what that's all about. This point here needs to go there. This point needs to go there. This one to there. And this one here will go out to 5 pi over 6. And now you can connect, and you have 1 period of that function. Does that make sense? And you could actually continue that way. Kind of that thing right there is going to mimic that portion of the curve there, right? And this might be a good kind of problem to look at. That was a cosine function, right? When I graph it complete like that, doesn't it look like it starts off like a sine function? So we could actually rewrite that flat curve that I have up there in regards to sine instead of cosine, if for some reason I thought that was necessary. Does that kind of make sense? A lot of different things you can do with these. We're just skimming the surface, hopefully developing some type of proficiency with them. Obviously, the more you use them, the better you get. I'm going to open up 6-3 at some point in the next couple of hours. Won't be due this week, be due next week some point. Thank you, too.